Good morning all. Myself Vigneshwari, Assistant Professor in the Department of Electronics and Communication Engineering from SNS College of Technology. So today I am going to handle the topic on adders from the unit combinational circuit. So this covers under the subject digital principles and computer organization. So basically an adder is a digital circuit that will be performing the addition of a 2-bit number. It performs the addition of a numbers that can be either two single bit numbers or multi-bit numbers also. So these adders have been classified as half adder and full adders, and further we have a ripple carry adder and multi-bit adders also. So today we are going to look only the half adders and the full adder part. So what is a half adder? Half adder is a combinational circuit that performs the addition of two single bit numbers, and they provide the result of either sum and also carry. So here A and B act as an input to the half adder circuit, and S refers to the sum and C refers to the carry. So the sum and carry is the output of such half adder circuit. So basically adders are being used for simple calculation. Half adders are being used for simple calculations because this covers only two 1-bit additions. And here you can see the logic circuit of the half adder. So here in the logic circuit, A and B are given as an input to the XOR gate, and the output is obtained as sum. And also A and B are also been given as an input to the AND gate, and the output obtained is the carry. So the sum and carry are predicted from the truth table of the half adder. So this is the truth table of the half adder where you can see the inputs A and B given different binary numbers. So when A is equal to 0 and B is equal to 0, so when you add 0 plus 0, the sum will be 0 and the carry also will be equivalent to 0. So when you provide the input A is equal to 1 and B is equal to 0, the sum will be 1 and carry is 0. And next, when A is equal to 0 and B is equal to 1, the sum is 1 and again the carry is 0. When you have both the bits A and B as 1, the sum will be 0 and the carry is 1. So this is 1 plus 1 is 2. The 2 is a decimal value, and when you convert to binary you get 10, and 0 is the LSB bit which goes and sit in the sum, and 1 is the most significant bit that accommodates the carry bit over here. And you can see in the right hand side the K map, Karnaugh map for the carry and the sum output. For carry, you can see 1 is obtained only when A and B is equal to 1. So from the K map, we will get the carry result as A into B. And for the sum, we have two categories of 1. So one is A and B are 1 and 0, and when A and B are 0 and 1. So for these two values, we get the sum output. So sum is equal to A B bar plus A bar B. This is nothing but an XOR gate. So A XOR with B, and hence we provide the result of A exclusive OR with B for sum and A dot B for carry. And the limitation when we speak about the half adder is, since as I already said that half adder is been suitable for addition of two 1-bit numbers. So the main drawback is you can have only the two inputs. You can add only two inputs, and therefore if any carry you are going to give as an input, it has been neglected and the process is hence incomplete. So to overcome this drawback, we are going with the next design of the full adder circuit, where in the case of a full adder circuit, we can perform an addition of three binary bit numbers where A and B are an input and Cin act as. Cin is nothing but a carry input, right? So we have three inputs, and same the sum and the carry are being produced as an output. So here to differentiate from the input carry, we are giving the output carry as C out. So you can see the logic circuit implementation of the full adder circuit, where A and B are being given to the input as an exclusive OR gate, and the output of A and B is being added as an input to another exclusive OR gate which obtains the input from the carry in. So finally you get sum as A exclusive B exclusive C in, and similarly carry out is nothing but A and B, and then your OR with C in of A XOR with B. So A dot B plus Cin of A exclusive OR with B. So you can see the truth table of a full adder circuit. So for full adder circuit, you have the input A, B and C in, where A, B, C are all three being 0, and you get the output as sum and carry is also 0. When you have the input A and B as 0 and carry in as 1, you get the output as carry as 0 and sum as 1. And same way, when A, B, C in are given as 0, 1, 0, you get the output carry 0 and sum as 1. And the next category, when A is equal to 0 and B and C in are 1, you will get the result carry 1 and sum 0, because 1 plus 1 is 10. As I said, 0 is the LSB bit that goes to the sum, and 1 is an MSB bit that goes to the carry bit, right? And when you see the last category, 1, 1, 1. So when you add 1 plus 1, 10, 10 plus 1 is 11. So for the last category, 1 plus 1 plus 1, which is 3, decimal value is 3. When the convert to binary value, you get the binary value of 11. So LSB bit goes as an occupies the sum, and MSB bit will be sitting in the carry. So we can see the K-map for carry and sum. The sum, it produces output 1 for A bar, B bar, C in, and A bar, B, C in bar, then A, B bar, C in bar, and A, B, C in. And similarly, the carry, it produces a result 1 when the data is AB plus A, C in plus B, C in. So this is how we obtain the result from the K-map and using the truth table, right? So this adder can also be implemented using the half adder circuit. So the first half adder, where we are using two inputs A and B, is given as an input to the XOR gate, which produces the result sum, and A dot B as a carry output. So this stage is being made as an output of the first stage is given as an input of the second stage. And the second stage, it also comprises of a similar another half adder circuit, where it takes the another input carry in and the output of the first half adder sum stage. And similarly, the carry of the first adder and the second adder are been given to the OR gate, and that is obtained of a say out. So this is how we implement the full adder circuit using the half adder. And the applications of this adder circuits have been used not only in the arithmetic and logical circuit, but they also been used in the core component like microprocessor, digital signal processing, for performing the arithmetic operation, and in the case of DSP for filtering and the convolution purposes. And still for more complex adder circuit, this has been acting as a basic building block. Right? The assessment questions have been discussed in the previous slide, so kindly go through the slides. Thank you.